In this lecture, we'll discuss the properties of a pure substance. Till now, we have discussed various laws of thermodynamics and applied them to various closed and open systems. The discussion till now in this course has been very general, that applies to any substance. In our examples, however, we have mostly considered ideal gases only. In general, for engineering applications, the working substance can be in different phases. For example, to perform thermodynamic analysis of a steam power plant that operates on water as the working substance, we require properties of water at various pressures and temperatures, where water will be in different phases, such as liquid and vapor phase. Similarly, in a vapor compression refrigeration cycle, the refrigerant will be in liquid and vapor phases. Therefore, it is important to study the properties of a pure substance in various phases. So, what do we mean by a pure substance? We have already discussed the definition earlier of a pure substance. A pure substance is one that has the same chemical composition throughout, that is, it has a single component. The pure substance may exist in different phases, but the chemical composition is same in all the phases. So water, carbon dioxide, helium gas, they are all examples of a pure substance. Sometimes mixture of gases such as air can also be considered as a pure substance as long as there is no phase change. But strictly speaking, that is not true. So we'll stick to this definition of pure substance with one that has a single component. Now let us investigate the properties of a pure substance, and because of the familiarity with water, let's take the example of water, and we'll need to use properties of water for analysis of a steam power plant, and therefore we are taking this example of water. So what we do is, let's consider a piston cylinder arrangement such as this. So the piston may also have weight, but you can also, let's say, put some weight on the piston. Now let's say that initially we have liquid water, let's say at 0.1 megapascal and temperature of 20 degrees Celsius in this piston cylinder arrangement. So the piston and the weight, they maintain a constant pressure. So throughout this experiment, the pressure will be constant because the mass and the weight of the piston will remain the same throughout the experiment. So now what we do is, we will add heat to this system and we'll increase the temperature of this system that has water, and at different temperatures we'll let the system equilibrate, and then we can look at the properties of the system. So we are looking at a constant pressure process. So let's plot this process on a temperature versus specific volume plot. So also consider that there is a unit mass of liquid, let's say 1 kg of liquid in this piston cylinder arrangement. Now initially we are at this pressure and this temperature, so the pressure remains same, but let's say we are at low temperature, so we'll call this state as state A. Next, what we do is, heat is transferred to water and a new equilibrium state is attained. So when we heat this liquid, its temperature is going to increase, but also its volume is going to expand. So we will reach to this particular state at the same pressure. So the temperature of the liquid will increase appreciably, but the volume, that is the specific volume, will only slightly increase. So we can keep on repeating this process. So we can repeat this process of heat addition and let the equilibrium be attained, and we can keep on doing this at the same pressure of 0.1 megapascal, and we can repeat this until, let's say, the system attains a temperature of 99.6 degrees Celsius. So at this temperature, if we look at our system, so what we will have now is, so our piston would have moved up because the specific volume has increased and there is still liquid but at a higher temperature of 99.6 degrees Celsius. Now, any further addition of heat would result in change of phase. So by that we mean that we will now have this liquid phase, but some part of water would now be in the vapor phase. So there's a change of phase after this point. Let's call this point as B. Now, if we add more heat and let the system attain a new equilibrium state, then some more amount of liquid will change to the vapor phase. So the volume is going to increase because the density of vapor is low, or the specific volume of vapor is high, but the temperature remains the same during the phase change process. So the temperature in this case would remain the same at 99.6 degrees Celsius for 0.1 megapascal pressure. So we will get these states that is represented by this horizontal line. If we continue with more heat addition, more liquid in liquid phase will keep changing to the vapor phase. Then a point is attained when all of this liquid is now in the vapor phase. So when the last drop of liquid vaporizes, we'll call that state of the substance, that is water, as this point C on this TV diagram. Further, if we transfer heat, it would lead to increase in temperature and specific volume, and now the vapor temperature is going to increase and its specific volume is also going to increase. And the specific volume is going to increase much faster with temperature than that for this liquid phase between A and B. And let's call this state as state D, when we have only vapor. So the temperature and pressure at which vaporization takes place, that is this temperature and corresponding pressure is 0.1 megapascal. This temperature and pressure are called saturation temperature and saturation pressure. So point B, where the liquid just starts vaporizing, is called saturated liquid, and point C, where the last drop of liquid vaporizes and the liquid has just completely vaporized and transformed to fully into the vapor state, this is called the saturated vapor state. Now if we further heat, we'll have this curve C to D, where the temperature of the vapor is higher than the saturation temperature. So these states between C to D and further, they are called superheated vapor state. Whereas between A and B, the state of the substance is in the liquid phase and its temperature is lower than this saturation temperature, therefore it is called a subcooled liquid. And note that the superheated vapor is this line where the temperature of the vapor is higher than the saturation temperature, and very highly superheated vapors are what we call as gases. Now what we do is, if the experiment is repeated at a higher pressure, so note that this curve is an isobar, and we consider this at a pressure of 0.1 megapascal. Now, if we repeat this experiment, let's say by putting more weight on this piston, then we'll get another curve. And this time, our curve would look something like this. So we'll start from this point where the substance is in the subcooled liquid state, then we attain the saturated liquid state, then there's phase change, and we have vapor and the liquid coexisting together at equilibrium state, and here all of the liquid is now vaporized and we have a saturated vapor state, and thereafter we have the superheated vapor states. If we keep on doing so, we'll get an envelope of these points, the saturated vapor and the saturated liquid states, which looks like a dome, and this is therefore called a vapor dome. So we can draw some more isobars. So we have isobars like this. Now at this point, if we draw an isobars, so this isobar would correspond to a pressure of 22.09 megapascal for water, and we see that as we keep on increasing the pressure, then this region where the liquid and the vapor phases coexist narrows down, and when we reach this particular pressure, there is no constant temperature vaporization process such as this. Instead, this isobar, let's draw it in red color, has a point of inflection over here at the top of the vapor dome and has a zero slope. So this has a point of inflection and zero slope at this particular point. So this point is called the critical point. At the critical point, the saturated liquid and the saturated vapor states are identical. The temperature, pressure, and specific volume at the critical point are called the critical temperatures, critical pressure, and critical volume. So whatever properties we have over here are called the critical properties. Above the critical pressure, the isobar does not go through this inflection point, it simply increases monotonically. Now above this critical point, the conditions are called the supercritical conditions, and we cannot identify the substance in liquid and vapor phases in this supercritical conditions. We simply refer it as a fluid. Now note that on this PV diagram, the isobars in the subcooled region, that is over here from A to B, are very steep because there is little change in specific volume of liquid upon increasing temperature. On the other hand, in the superheated vapor region, the isobars are not that steep because there's a considerable change in the specific volume with an increase in temperature while keeping pressure constant. So now let's look at another experiment, a similar experiment, but this time we are going to keep temperature constant and we are going to vary the pressure. So we have the same substance, that is water, and we can vary the pressure by keeping more mass every time on this piston, and we'll keep this system in contact with some thermal reservoir with fixed temperature. It could be a liquid bath, let's say a very large liquid bath whose temperature does not change, and therefore the temperature of the reservoir and that of water would be the same. So we are keeping same temperature, but now we are varying the pressure, and that is because we can now look at the various phases of water on a PV diagram for a fixed temperature. So temperature is constant. So now we are going to plot isotherms on this PV diagram. So the PV diagram looks something like this. Again, we have this dome within which we have liquid and vapor coexisting. That means if we choose a pressure and specific volume over here that lies between the vapor dome, then water would be partly in the liquid phase and partly in the vapor phase at equilibrium. Now consider that initially we are at this state, that is D, and this is same state as this, that is for a superheated vapor state. So we have initially in this piston cylinder arrangement water in superheated state, and we have denoted it by point D, and we'll denote the same points as what we have in this TV diagram on this PV diagram. So now what we do while keeping temperature constant, so these are all isotherms. So while keeping temperature constant, let's increase the pressure. So if we increase the pressure, the specific volume of the superheated vapor is clearly going to decrease as we increase the pressure. And what we are showing over here are all the equilibrium states. And if we continue this process of increasing the pressure, we'll reach this state C, where the substance is in the saturated vapor state. Now, if the compression is continued, now we'll start having condensation. So, between C to B, we will again have some part of water in liquid phase and other in the vapor phase. So condensation will happen at constant pressure. So this is a constant pressure, and we are plotting an isotherm, so it is at constant temperature and constant pressure, that is the saturation temperature and saturation pressure. Now we can continue this process until we reach point B, where substance is in the saturated liquid state, that is all the vapor is now condensed to the liquid state. And thereafter, if we increase pressure, now we have a purely liquid phase over here, and this phase is called the compressed liquid. So the subcooled liquid phase and the compressed phase, because these points A and A are the same phases. So when we look at a PV diagram, then we call this state over here, for example state A, as the compressed liquid state, because the pressure is higher than the saturation pressure that is corresponding to this horizontal line for this particular temperature. Now again note that the pressure between these points A and B is very steep, and that's because to compress a liquid a large amount of pressure is required. So for a small change in the specific volume between A and B, you would need a very high pressure to take the liquid that is at the saturated liquid state at B, and if we want to go to state A, we need to apply very large pressure, and there will be very small change in the specific volume as we go from B to A. Also note that again the apex of this vapor dome is the critical point, and above this we have the supercritical state. So what we have seen on this TV and PV diagram, we have seen the states where we have this substance, for example water, in liquid and vapor phases only. We've not considered the solid phase region, and that's for simplicity and also for engineering applications that we're going to discuss in this course. We'll mostly be dealing with liquid and vapor phases. However, note that on a PV diagram at low temperatures, so note that here the isotherms for higher temperature lie above. So in this region over here, that is low temperature region, there is a solid vapor region that is below this liquid vapor region. Now in the solid vapor region, the isotherms have same general character as this vaporization curve. So you have same phase change occurring at constant temperature and constant pressure, where solid and vapor phases can coexist. This horizontal isotherm in the solid vapor region would represent the isobaric transition from solid to vapor, that is called sublimation. And between the solid and vapor phases and this liquid plus vapor phases, we'll later see there is a line that separates the solid plus vapor region, where the solid and vapor region coexist, from the liquid and vapor region. And this line we'll see soon is where the three phases can coexist, and it corresponds to the triple point. So for water, the triple point is at 273.16 Kelvin at 611.73 Pascal pressure, and we look at this triple line shortly. Just as we have the solid and vapor region, we also have a region over here where the solid and the liquid phase would coexist. For example, the water can be in ice and the liquid states. And also note that we have these isotherms corresponding to higher temperatures, they lie above, because you can see that for a given specific volume, if you have a higher temperature, then the vapor, for example over here, will have higher pressure. Therefore, isotherms corresponding to higher temperatures lie above. Now that we have seen the TV diagram and the PV diagram for water or any substance, because even if we don't have water, typically you would get the similar behavior, only the difference would be the difference in the values. But qualitatively, even if we consider, let's say, carbon dioxide, we would get a similar TV and PV diagram for other gases and other pure substances. So now having looked at PV and TV diagram, let's look at another diagram, and this time we look at the P versus T diagram. And this diagram is also called the phase diagram. So what we do is, on a P versus T plot, we'll plot these pressures and temperatures. You can just look at this PV diagram, or you could look at a TV diagram. So let's say we'll plot this pressure and temperature where, let's say, the liquid and the vapor phases coexist. So if we do this exercise, so let's plot this pressure versus temperature. So all these points B to C will collapse on to a single point because we are just plotting pressure and temperature where liquid and vapor phases coexist. And we'll have another point such as this over here corresponding to this line. So we'll get a curve something like this, and this would go on until we reach this critical point on this PV diagram. So this curve will end at the critical point. So note that this curve is the vaporization curve because at these pressures and temperatures corresponding to this line, we have liquid and vapor phases are coexisting and there is phase change between liquid and the vapor phase. Similarly, if we plot the pressures and temperatures where the solid and the liquid phases coexist, for water we'll get a curve something like this, and this curve is called the fusion curve. And similarly, if we plot those pressures and temperatures where the solid and the vapor phase they are in equilibrium with each other, we'll get the sublimation curve. So all these curves, the fusion curve, the vaporization curve, and the sublimation curve, they intersect at this point. This is the point where the solid, liquid, and vapor phases they coexist, and therefore this is the triple point. So note that for a PV diagram, we have this liquid vapor region between these saturated liquid and vapor states, but on a PT diagram all these states they collapse onto a single vaporization curve. Similarly, all these solid and vapor states they collapse on to the sublimation curve, and solid and liquid states they collapse on to this fusion curve. Away from these curves we have only single phase equilibrium states. So what we have is we have the substance is in purely solid state at these pressures and temperatures. Here it is in the liquid state and here it is in the vapor state. So sometimes we can say that if the vapor is beyond this critical temperature, we typically call that state as a gas. So the properties of a vapor and a gas are same, except that gas which is above this critical temperature, it cannot be liquefied upon isothermal compression. That means if we are in this supercritical state and we increase the pressure, we are never going to liquefy this gas. So one important thing to note on this phase diagram, that is the PT diagram, is that the slope of the sublimation curve and the vaporization curves are positive, but the slope of the fusion curve may be positive or negative. For water, it is negative, but for other substances, let's say for, so this is for water, and let's say for carbon dioxide, we would have a positive slope for this fusion curve. So the positive slope of this vaporization curve means that if we increase the pressure, then the boiling point of water is going to increase. On the other hand, if we look at this fusion curve, then let's say we are initially at this state, and if we increase the pressure, then the temperature at which phase change would occur, that is where the ice would melt, would go down. Therefore, the melting point of water decreases with an increase in pressure. And this negative slope of fusion curve for water is because water expands upon freezing. So the slopes of these curves, that is the coexistence curves, is given by the Clapeyron equation. Again, note that the triple point on this phase diagram is represented by a single point, but if you look at a PV diagram, then the triple point is represented by a line, because the specific volume can vary while the pressure and the temperature remains fixed at the triple point. And that's because the substance, such as water, can be partially in liquid, solid and vapor state, and for a given mass of substance you could have different amount of liquid, solid and vapor phases. Therefore the specific volume can change, but the pressure and temperature at the triple point would be fixed, because there the phase is changing. This diagram shows the phase diagram for water for a wide range of pressure and temperatures. So we have seen this part in our discussion till now, where we have the vapor phase, liquid phase and the solid phase, which we call as ice 1. But at low temperatures and high pressures, water may be present in different solid phases. For example, ice 2, ice 3, 5, 6 and other solid phases. Therefore, a pure substance such as water can have a number of triple points. So this is one triple point where we have solid, liquid and vapor phases that are coexisting. But here, if you see, we have one solid phase, another solid phase and the liquid phases are coexisting. So all these are the triple points, but there is only one triple point where we have solid, liquid and vapor phases that coexist. Next, let us discuss the PVT surface. So what we have shown till now is we can have the data represented on TV diagram, that is data of different equilibrium states that a substance can have. This we've discussed keeping in mind water, but any substance would have similar TV, PV and PT diagrams. So we've looked at PV diagram, PV diagram and we've looked at P versus T diagram. But all these diagrams can be consolidated in form of a PVT surface, where we can plot pressure, temperature and the specific volume on a three-dimensional plot, where P, T and V are plotted on the orthogonal axis. And if we do so, then we get this surface in the pressure, volume and the temperature space, and each point on this surface corresponds to an equilibrium state, and we get this surface, that is the PVT surface, because the state of a pure substance, as we have discussed earlier, can be described only by two independent intensive properties. So if we choose temperature, and let's say this is specific volume or volume for a given mass of a substance, then the pressure cannot vary independently. So if temperature and specific volume are taken to be independent, then pressure would depend upon temperature and volume, and that's why every equilibrium state can be represented on this PVT diagram for a pure substance. And this is a PVT diagram for a substance like water that expands on freezing. And the TV diagram, the PV diagram and the PT diagrams that we have described earlier are simply projections of this PVT surface onto the different planes. For example, here what we have is we have this PVT surface, and if you project this surface on this pressure versus temperature plane, then you get the PT diagram that we have discussed. Similarly, if you project this surface on a PV plane, then you would get the familiar PV diagram. Similarly, if you project this PVT surface on the temperature versus volume plane, then we would get our familiar PV diagram, and these would be the isobars, where the pressure is constant on this TV diagram, and there would be many such isobars. So whatever diagrams, the PV diagram, the TV diagram, and the PT diagrams that we've seen are just the projections of this PVT surface on the different planes. So this PVT surface that we are showing is for a substance that expands on freezing, such as water. And similarly, we'll have a PVT surface for a substance that contracts on freezing, and typically substances contract on freezing, and one example of that is the surface for carbon dioxide. So on this PVT surface, such as for the carbon dioxide, if you look at this line, this is the line for vaporization, where the liquid and the vapor states, they coexist. But when you look at the projection of this surface on the PT diagram, all you get is, for this line, is a single point. Similarly, for this line, you will get another single point. Similarly, for this fusion curve, and for this sublimation curve, you will get single lines, although you have various states on this solid vapor coexistence line and this vaporization curve. Similarly, the triple point, that is this particular line, and there's only one triple point line that actually will project onto a single point on this PT phase diagram. So for a substance such as carbon dioxide that contracts on freezing, if let's say we are over here, and for a fixed temperature, if we start increasing the pressure, what we'll have is, let's say initially we are in the vapor phase, then we'll go to the liquid phase, and eventually we'll go to the solid phase. But for the substance such as water that expands on freezing, let's say you are over here, so initially you are in vapor phase, then for a fixed temperature, if you increase the pressure, you may go to the solid phase, and then you will go to the liquid phase, and that is also shown over here. So if you look at this isotherm, so you start at this state A, that is the vapor phase, then you follow this isotherm because the temperature is constant, then you have this solid plus vapor phases that coexist below the triple line, and here the substance is at solid state, and then from solid you go from D to E, and here you have the liquid state. That is, this substance first goes from vapor to solid and then to the liquid phase, and this is only because we have this negative slope of this fusion curve on this PT phase diagram. Finally, let's look at the PVT surface for water for a wide range of pressure and temperature. In this case, we not only have the liquid, vapor, and the solid phase, that is the ice 1 phase, but we have many other phases. So what you need to note is that any point on this surface corresponds to given temperature and specific volume, and there is a unique pressure, and this point corresponds to an equilibrium state, and all these points correspond to an equilibrium state. And by looking at projections of this PVT surface on these planes, such as this PV plane, you would get the PV diagram. Similarly here, you would get the PT diagram if you project this surface on this plane, and if you project this surface on the top plane, you would get the temperature versus specific volume diagram. To summarize, in this lecture, we've looked at the properties of a pure substance, and in particular, we've looked at how these equilibrium states can be represented on a PV, TV, and PT diagrams, and in more general, the PVT surface. And we'll continue this discussion on the properties of a pure substance in the next lecture.